given y equal, or let's say dy dx equal p times y. So given a differential equation, if I want to solve this, I could use separation of variables. Dy over y equals p dx. I can integrate. Natural log of absolute value of y equal px plus c. And I could say y equal e to the px plus c, or simply e to the px times e to the c. All right, let's get that right. And I could say that's c times e to the px. That would be my solution. So y equal e c times e to the px would be a solution to this differential equations. If I'm looking at a linear differential equations with constant coefficients, so p of x is a constant, not a function of x, a constant. I could take this equation and I could say, if this is true, I could say let y equal e to the dx. Then, to solve this equation, I need a derivative. Well, y prime is e to the dx times d, where d is a constant. So if I fill in the blanks, d e to the dx equal p times y is e to the dx. If I get everything on one side, 0 on the other side, factor e to the dx out. Well, we know that e can never equal 0, so it must be that d minus p equals 0, and d must be a p. So my solution to this equation would be y equal any multiple of this. And remember, d was px. And you notice I got the solution without using calculus. I got the solution just by simply letting y equal e to the dx. So if I look at a higher order, in chapter 11 we used first order. Now we're talking about any order. Higher order linear differential equation. If you look at any order, n order differential equation, and just one tiny mistake there, I'm so used to dx. If those coefficients right there, if all of those are constants, then here's the key. Let y equal e to the dx be the solution. If this function right here is 0, then we say this is a homogeneous differential equation. If this doesn't equal 0, we say this is non-homogeneous. In 12.1, we're going to deal with homogeneous differential equations. Well, let's test this theory. We're looking at the first problem we want to solve, and it says solve the differential equation. This is a linear differential equation with constant coefficients. What does that mean? That's a 1, that's a 5, that's a 4. If that's the case, let y equal e to the dx. What do I need here? There's a y, that's good. I need a derivative. Well, no problem. Y prime is d e to the dx. What's d? A constant. And I need a second derivative. Y double prime would be d e to the dx. If I fill in the blanks, that is, if I replace this by d, oh, that's d squared, isn't it? We'll take another derivative. Plus 5, y is d e to the dx, plus 4, and y is simply the original. And you'll notice they all have e to the dx. I'll factor e to the dx out of them. I'm looking at d squared plus 5d plus 4 equals 0. By the way, this is called the characteristic equation. And now what? Now I do know that e to the dx can never equal 0. So it must be that d squared plus 5d plus 4 equals 0. It must be d plus 4 into d plus 1 equals 0. So d must be a negative 4 or a negative 1. Which means my solution would be e to the d, e to the negative 4x, and the other d is e to the negative x. Any multiple of those will do. And I'll say the general solution, this is the solution set, which means any multiple of those, y will equal any multiple of that, some c1 e to the negative 4x plus some c2 e to the negative x. Those would be a solution. First, the second, or any combination will do. So, what are we doing here? We are solving not a first derivative, we're solving a second derivative without using calculus. By letting y equal e to the dx. What's the catch? This is a second order linear differential equations with constant coefficients. If that's the case, let y equal e to the dx be a solution. I need y, it's right there. I need two derivatives. Well, first derivative is e to the dx times d, and a second derivative is e to the dx times d, which is, and if I fill in the blanks, I'm looking at d squared e to the dx minus 9 e to the dx equals 0. You factor out e to the dx, that's d squared minus 9 equals 0. That means e to the dx equals 0 can never happen. Or d squared minus 9 equals 0, that means d equal plus or minus 3. What does that mean? That means the solution set is e to the positive 3x and e to the negative 3x. That's the solution set. And the general solution, y equal some multiple, any multiple of e to the 3x plus any multiple of e to the negative 3x in any order. You can put them anywhere you like. Oops. General solution. This is called the homogeneous solution because this is a homogeneous linear differential equation. They call it complementary. It has many names. We're not going to worry about that yet. Now again, I look at this. This is a linear differential equation, and we have constant coefficients. And this is second order. It doesn't matter what order it is. If this is the case, you let y equal e to the dx be a solution. I need two derivatives. First derivative, d e to the dx. Second derivative, d squared e to the dx. So 6 d squared e to the dx minus d e to the dx minus e to the dx equals 0. You'll notice they'll always have e to the dx. And we know that e to the dx can never be 0. So it must be that 6d squared minus d minus 1 equals 0. That indicates that 3d and 2d minus 1 plus 1 equals 0. So d is negative 1/3 or positive 1/2. So the solution set is e to the negative x over 3 and e to the t over 2. That's the solution set. And the general solution, y equal any multiple of this, and again, it doesn't matter which one you write first, and any multiple of that. You have to forgive me, I'm so stuck on t. So, this is called the homogeneous solution or the complementary. We're not going to worry about the naming yet until a few sections from now. Next problem on the list. Again, this is a linear equation, second order. It doesn't matter which order it is, but it has constant coefficients. We let y equal e to the dx be a solution. I need two derivatives. Y prime is d e to the dx. Y double prime is d squared e to the dx. So the second derivative is d squared e to the dx plus 4 times, a derivative is right there, d e to the dx plus 1 e to the dx equals 0. Factor out e to the dx, d squared plus 4d plus 1 equals 0. So e to the dx can never equal 0. It must be that d squared plus 4d plus 1 equals 0. That doesn't factor, not to worry, it's quadratic. We dealt with that way more than we like. Take half of the middle number, which is 2, and square it. And d plus 2 squared will equal 3. Square root both sides. You pick a plus or minus. D plus 2 equal plus or minus radical 3. And d would be negative 2 plus or minus radical 3. So the solution set is e to the dx, but d is this mess, so e to the negative 2 plus radical 3x, e to the negative 2 minus radical 3x, and the general solution of the homogeneous, y equal any multiple of that plus any multiple of that. So what's the deal in this section? You get a quadratic in which you have two distinct solutions. So far, there we go. How about the next problem? Again, this is a second order linear differential equation with constant coefficients. I would let y equal e to the dx. You have to show me that on every problem. I insist on that. I know you're going to get sick of that, but I'm not going to stop. You're going to have to show me this on every problem that you do. So second derivative is right there, d squared e to the dx plus 2. The derivative is d e to the dx minus 5 e to the dx equals 0. If I factor e to the dx out, I'll have d squared plus 2d minus 5 equaling to 0. E to the dx equals 0, never going to happen. It must be d squared plus 2d minus 5 equal to 0. That doesn't factor, not to worry, you could use quadratic formula. I prefer completing the square. Whatever you did in the first half of this class, when you did parabolas, ellipses, hyperbolas, you complete the square. Take half of the middle number, which is 1, and square it. So this says d plus 1 squared equal a 6. D will equal, if you square root both sides, plus or minus radical 6 and move the 1 over. The solution set is e to the negative 1 plus radical 6 times x, e to the negative 1 minus radical 6 times x. And the general solution is y equals c1 times, it doesn't matter which order you put those in, plus c sub 2 e to the negative 1 minus radical 6 x. Let me move the rest up. So what they do in differential equations, they skip this step for you. They say, look, let's jump you straight to this. If you're looking at this, you should know that what this means. This means you had the second derivative of y with respect. If you really would rather write y double prime, you can. This says you took the second derivative of y minus 2 times a derivative minus 3y equals 0. That was the original problem. Either way, you're going to let y equal e to the dx. And they did the work for you. If you let y equal e to the dx, then you're looking at d minus 3 into d plus 1. And y is e to the dx equaling 0. Well, e to the dx cannot equal 0. It must be that d minus 3 into d plus 1 equals 0, which indicates that d must be a 3 or a negative 1. So the solution set is e to the 3x, e to the negative x, and the general solution is y equal any multiple of those. So c1 times e to the 3x plus c sub 2 e to the negative x. So they save you the work on that, and they deal with that a lot. Again, they're saving you all the steps. What this, and you don't have to write this, I'm writing this so you know what it is. This is really saying you must have taken the third derivative minus twice the second derivative minus a derivative plus twice y equals 0. Or you were looking at y triple prime minus 2y double prime minus y prime plus 2y equal to 0. Well, here, it's a third order differential equation. Doesn't matter with constant coefficients. They already let y equal e to the dx. That's how they got that. So this is the characteristic equation. Well, factor. Take, you could, of course, you don't need any of this. This is just me explaining what they're doing, so you really don't need that. You could say, well, if I factor a d squared out, d minus 2 minus d minus 2, right? All applied on y, which is e to the dx. Then you could factor a d minus 2 out. You'll have d squared minus 1 times e to the dx equals 0. So d minus 2 into d minus 1 into d plus 1, e to the dx equals 0. E to the dx can never equal 0. It must be that d equal a 2, a 1, or a negative 1. The solution set is e to the 2x, e to the x, and e to the negative x, which indicates the general solution is y equal any combination of those c1 e to the 2x plus c2 e to the x plus c3 e to the negative x. And that would be my final general solution. Almost done. How about here? Well, here we know the drill. We know they let y equal e to the dx. That's how they got this. And we know this is really d minus 2 into d plus 1 y. Well, y is actually e to the dx. That's how they get the d. We know e to the dx cannot equal 0. So it must be that d equal 2 or negative 1. So we know that the general solution is e to the 2x, e to the negative x. I mean the solution set. This has a different name. We'll talk about it later. And the general solution is y equals c1 e to the 2x plus c2 e to the negative x. That is my general solution. And when we say if x equals 0, y equal 1. If x equals 0, if I put a 0 there and a 0 there, y equal 1. 1 equal c1 times e to the 0 plus c2 times e to the 0, or negative 0. So this says c1 plus c2 equal 1. And what does this mean? D sub y means take the derivative of y. So d sub y is really the derivative of y. Well, what's d sub y right there? D sub y would be, the derivative with respect to y is y prime, and that is 2 c sub 1 e to the 2x minus c sub 2 e to the negative x. And when x equals 0, because e to the 0 is 1, that is a 2. So I'm getting 2c1 minus c2 equal a 2. I have two equations, two unknowns. If I add those, wouldn't those cancel out? And I'll get 3c sub 1 equal 3, c sub 1 equal 1. Very good. Go to the first equation and say c1 plus c sub 2 equal 1, so c sub 2 equals 0. Plug those in. Y would equal c sub 1 is 1 times e to the 2x, and if you put a 0 there, wouldn't that be the explicit solution satisfying those two conditions? And that would be it for this section.